All right, welcome back, everyone. So, as you'll recall, we've begun to get into the issue of the reactivity of protons that are alpha to carbonyl groups. And we've pointed out that they are, in general, slightly acidic and can be pulled off with a suitably strong base. And we've also pointed out that also under acidic conditions, carbonyl compounds with at least one alpha proton can enolize. So now it's time for us to get into some of the reactions that these species can undergo. One very standard one that occurs in acidic solution, although it can be done in alkaline solution too, involves enolizable aldehydes and ketones, meaning that they have at least one alpha proton, and their treatment in acetic acid with a halogen, chlorine, bromine, or iodine. My understanding is any of those three will work. Fluorine will probably start eating the glass of the flask before it does anything useful and controllable, but chlorine, bromine, and iodine are all give clean products. And just to give an example here I've taken cyclohexanone, and if you were to treat this with one equivalent of bromine, elemental bromine, in acetic acid solvent, I'd expect that we would replace one of those four enolizable protons with a bromine. And of course, if you used an excess, you would need at least four equivalents. I'd expect that you would brominate all four of those positions. So you'd replace all enolizable protons with bromines. And my expectation is it wouldn't touch any of the other six protons. So to use more than one equivalent, but under four equivalents of bromine in a case like this wouldn't be a very good idea. I don't think you'd get anything useful out of that. You'd get a mixture of 0, 1, 2, 3, and 4 bromines. You just get a mess. You'd get all possible compounds. But I would expect one equivalent of the halogen would be a clean reaction, and excess halogen would also be a clean reaction. And we'll get into this mechanism shortly. What was I going to say? Oh, and of course, if bromine were replaced with chlorine or iodine, well, then you'd wind up with the corresponding halogen, of course. So this can be a fairly useful reaction, actually, because once you put that halogen in there, well, there's all kinds of things you can do then with that halogen. The mechanism, how would excess bromine look? Would have to say excess bromine. I mean, what would you be given? It would say excess bromine. Or I guess you could put like 4 equivalents in this case, right? Because that's the maximum. You need at least 4. But anything under that, but more than one equivalent, would not be a good reaction because you'd get a mixture. Oh, like the product. Oh, okay. Well, yeah, we can do that. The one that you'd get from excess bromine, I figure, would look a little something like this. But again, I'm just using cyclohexanone here as an example. Actually, I might be able to bust a move over there in just a moment. Let's see. So that's how the product would look. Let me see. Oh no, because this is all one big thing, isn't it? Yeah. Well, let's see if I can manage it anyway. Oh no, I meant over here. Eek. Okay, we can make this work. here's how we're going to manage this. And of course, this would be excess bromine. In glacial acetic acid or pure acetic acid. So yeah, there's no water or anything else. I would expect with this, it would just be pure acetic acid as the solvent. Good, so something like that. And of course, as you see, we're totally fine drawing it like this. There's no chiral carbons, right? Those two carbons both have two bromines on them, so they're not chiral. But those are the only two ways to do it that I can think of that are at all useful. In terms of the mechanism, there is always a carboxylic acid group. Are there other options for this reactor? Does it have to be a carboxylic acid group? Oh, this one, oh, wait a minute. The solvent is acetic acid. Oh, can you use other solvents? That's a good question. I mean, I think you would need it to be protic because we're going to have proton transfers, as you'll see in a moment. But I think you want it to be at least somewhat acidic. So could you do it like that in water or methanol? I don't think so. I've never heard of such a thing being done. Because when you look at the mechanism, as we're going to get to, we're relying on acetic acid being at least a little bit acidic, because we're running this under acidic conditions. So it's a good question. I don't know if I 100% for sure know the answer, but my gut reaction is no. It has to be acetic acid. And I don't think you'd use a carboxylic acid other than acetic acid, just because acetic acid is so cheap and plentiful. So that would be my take on it. Hopefully that's at least somewhat helpful. Anyway, since we're under acidic conditions, we know that because acetic acid is at least a little bit acidic, not the strongest acid in the world, but that means we would expect to be doing things on the acidic side of the ledger. That means we would want to protonate our carbonyl oxygen first. And yes, like I said, acetic acid isn't the strongest acid in the world, but it's good enough. I think it's reasonable to invoke acetate ions in acetic acid solvent. It's not a strong acid. It's not going to be 100% or anything near that ionized, but I think you would get a reasonable enough concentration that the mechanism makes sense. Once you've done that, you can use an acetate ion, of which there will be a few, to form the enol. And having done that, we already talked about how enols as well as enolates can act as nucleophiles. The driving force in this step, I would say, is breaking that weak halogen-halogen bond. Of course, the mechanism would look identical if it were chlorine or iodine. You're just changing the identity of the halogens then. And as a result, you'll get simply your the product, except it's protonated. Now all we need to invoke is another acetate ion to pull off that proton. Again, there's not going to be a really hugely high concentration of acetate ions, but with acetic acid being the solvent, I think that's good enough. You certainly would have some acetate ions that pulls off the proton, and we're done. And if we were then to go on with excess, you would one by one, in no particular order, replace all of the other three hydrogens with bromines. So the mechanism looks something like that in acidic solution. I think that's a reasonable way to draw it. So, but this is already in your class notes, or at least it should be. I just opened your class notes now and there it was, so should be. So, but I would expect this to be pretty general for any aldehyde or ketone, as long as there's at least one proton alpha to the carbonyl group. If not, then it's not enolizable and game over. There's no possible way you can get a reaction. Hopefully, whoever thought of it wouldn't even try once they realize it's not ionizable. So that's how you replace alpha protons with halogens in the case of aldehydes and ketones. And this can again be a somewhat useful reaction because halogens are things that you can use to put in other functional groups. But normally we're going to be interested in putting something a little bit more maybe refined there, putting in alkyl groups via SN2 reactions. Though honestly, this is almost kind of an SN2 reaction. You're kind of picking up Br plus and you're expelling the bromide leaving group. So, and those mechanisms will be very much the same. And I think those will largely be the topic on Friday. We're going to talk about various alkylation reactions, but certainly this is a possibility. At least that's what I would say. Questions on this mechanism? And like I said, that's already in your class notes. So where are we at? 5 minutes to 11 about. So just set this up here. Actually, I don't think I wanted to do that, because I want to leave those kind of headlines. Let's just do this. Okay, very good. So it turns out to be possible to do the same type of thing to carboxylic acids as the starting material, but they're a good bit less reactive than ketones and aldehydes, so we need to get out the heavy hammers. We need to use much more reactive species. And there, the reagent of choice turns out to be phosphorus tribromide, which has a couple of different actions, basically. So let's start with that compound. You may call that phenylacetic acid if you like. Everyone will know what you mean. And this is a two-step process. The first step uses bromine and phosphorus tribromide. And I should mention, as I did in the heading up here, I don't know, I'm not aware of any way to chlorinate or iodinate in the alpha position. I believe this can only be done with bromine and phosphorus tribromide. In other words, not iodine and phosphorus triiodide or chlorine and phosphorus trichloride. My understanding is this has to be bromine. And then after that, this does, why does it keep doing that? After that, this does require an aqueous workup step. So again, notice it's 2 steps. And let's see. Actually, if you don't mind, normally we wouldn't draw this intermediate if you know, if we were just being asked for the product, let's say. But I do want you to be aware that this goes through the acid bromide. The action of the bromine and phosphorus tribromide is going to be twofold. First of all, I'm just going to replace that with CH3 for the moment. The first thing it will do, and again, assuming one equivalent of the bromine, the first thing it's going to do is replace, there we go, replace one of those alpha protons with a bromine. And again, if we used an excess of bromine, I'd expect it would replace both of them. But it will also convert the carboxylic acid to an acid bromide. So you will wind up with this for a short time, at least until you do your acid workup. So that's the equivalent, I'm sorry, your aqueous workup. And this is why you need that aqueous workup, because acid bromides are really, really reactive, and they're not in general going to be something that you can isolate too easily. So you will want to hydrolyze the acid bromide and convert it to carboxylic acid. That's generally the whole reason beyond why we're doing this in the first place. There we go. And so from that, we'll get the carboxylic acid functional group back. And again, if instead of just one equivalent of bromine we'd used in excess, then I'd expect that you'd get 2 bromines there. But again, it will only touch the ones that are alpha to the carbonyl group. So you're not responsible for the mechanism of this reaction. It says it right in your class notes. I mean, I guess I would like you to be aware that this does go through the acid bromide. However, the final product is not going to be that. Wait, how do we have 2 first steps? That's better. And one would always and necessarily have that aqueous workup step. So of course, if I were just being asked for the product, I wouldn't even draw this. I just put it in there just to make you aware. Certainly the final product would be this. Or again, if it said excess bromine, then you'd have 2 bromines over here, kind of like we did up here, where we replaced all enolizable hydrogens. Of course, I just noticed another thing, and probably a lot of you did as well. In so doing, we did just make a chiral carbon, where previously there was none. Of course, that carbon right there is chiral. So I'd expect with just one equivalent that you'd get a racemic mixture of the R and S bromides. And again, especially watch Owl Like a Hawk, so that you're aware of what kind of answer they want you to give. But not including stereochemistry, that would be the product with just one equivalent of bromine. And this is now pretty cool. We're actually 1 step away from making phenylalanine. Oh, no, we're not. I lied. We need 1 more carbon to make phenylalanine. I'd have it to start with phenyl CH2CH2, CO2H. And would that even work? Yes, of course. Yep, that would work. But if we had 1 more CH2 in the middle here, we could now treat that with an excess of ammonia, and you'd get a mixture of DNL phenylalanine. So this compound would not give you a naturally protein-bound amino acid, but you can make amino acids using this type of method. So that's something useful that you can do with these things. But that's basically it. Like I said, you're not responsible for the mechanism. Although you could probably come up with one that's not too outrageous without too much work. Good, everyone okay with this one then? I feel like this is going especially quickly today. Because we were only, wait a minute, I just want to make sure. Right, I think I figured out what we're going to do today. Even though we were only technically listed to do sections 4 and 5 today, or rather sections 3 and 4, I think what would make the most sense, just because everything would wind up in the same place, let's talk a little bit about enolate ion formation. That is, treatment of aldehydes and ketones with strong bases to give the enolate ions. And then, that's what I thought. Yeah, next time we can do all this acetoacetic and malonic ester stuff, just alkylation of enolates. But there's something else that your book doesn't mention, or at least does not make a big deal out of, but it is a big deal. It's this whole thing of kinetic versus thermodynamic control with enolate formation. And it's a huge hole that you really can't have a complete coverage of this material without going over that. So I think that would be good for us to cover also. And then that's fine. We can save all the alkylation stuff for Friday. Good, so I think, actually what I'll do is I'll open a new document. So what about enolates? How do you make them? Well, let's just leave it at enolate formation. We'll leave reactivity until next time. So in order to make an enolate, one would first need, you first need an enolizable aldehyde or ketone. So maybe we'll go back to our cyclohexanone. We'll just use that as an example. And of course, cyclohexanone has no fewer than 4 enolizable hydrogens, 2 on this side of the carbonyl and 2 on the other side. And all we need is a sufficiently strong base to pull off one of those 4, in this case, equivalent protons, and we'll have ourselves the enolate. That looks a bit screwed up. Sorry, but I'm picky. So that's where our 4 enolizable hydrogens will be. And in the class notes, I've given some examples of bases that are strong enough to do that. A couple that we know already are the hydride ion would certainly do it. Certainly sodium amide, NaNH2, which is really NH2 minus, will certainly do that as well. One particularly commonly used, yeah, I learned other things I can do with ChemDraw that I didn't know I needed. One particularly common base that will, a commonly used base that will do the job for us is something called LDA, which is short for lithium diisopropyl amide. And I'm, of course, here not using the correct geometry on the nitrogen atom. It's not actually linear, of course. Rather, I would expect that nitrogen to be sp3 hybridized. But you get the idea. This is, oh, and this is sold commercially most often as lithium salt. There we go. So that compound over there, let me just find its own place, get it out of the way over here. Or better yet, let me actually move that there. So this is quite often used as opposed to a metal hydride base or sodium amide or something like this. And this guy is LDA, which stands for lithium diisopropyl amide. And it is strange that that word amide is used. Of course, we're not referring to the functional group, but amide in this case means that you're looking at the conjugate base of an amine. So that's a very common one. And there are other reagents that are like that. If we have time, I might tell you about a few of them. There's one in particular that has an extremely amusing name. But more to the point, if we treated this compound with, let's say, LDA, and you want something aprotic, obviously, anything protic, we'll just put the proton back on the conjugate base of the amine. Diethyl ether is pretty common. That's kind of our go-to aprotic solvent. And so what would happen? Well, I would expect that this species would pull off one of those 4 protons. Doesn't matter which, they're equivalent. I'm going to choose to go for that one. And you would wind up making your enolate. And by the way, I would expect that that would be quantitative. Could you use something like a hydroxide or alkoxide base? Yes, but then it wouldn't be quantitative. You'd only just get a little bit of the enolate at any one time. And that's now something that we could use to our advantage, which is what I'm going to point out in that addendum at the end of the chapter. But if your goal were to get the enolate quantitatively, in other words, to deprotonate effectively all of the carbonyl compound, then you need a really strong base, either sodium hydride or sodium amide or LDA, something like that. And at once you have your enolate, now there's 1,000 things we can do with this. A couple dozen of which, or just a few of which, we'll cover on Friday. This now is going to be a really outstanding nucleophile. And certainly you could treat it with an elemental halogen, like bromine or iodine. And so you can do halogenation in alkaline solution just as well as you can in acidic solution. You could also treat this with pretty much any alkyl halide you like, preferably primary, of course, and you'll get an SN2 reaction. And last but not least, you can use this as a nucleophile and treat it for an electrophile with a different carbonyl compound. Welcome to chapter 23. That's your aldol and Claisen condensations and reactions that are like that. But that's chapter 23. We'll wait on that. So next time we'll go over all of the different ways in which one could use this to alkylate here at this position. You would not even be, by the way, of course, that other hydrogen is still there. I just didn't show it. But you might want to ponder that before class time, before class next time. Let's say that we treated this with I don't know, 1-bromobutane. What would the product look like? And if maybe even if we have time at the end of class today, we'll go over that one. Since I do see that we're going to have extra time, I don't know why this is going so quick. I feel like I'm moving through molasses today. I don't know why I'm so sleepy. I am sorry about that. I like to be a little bit more perky than this, but it is what it is. Maybe before we go on, though I don't know that I really care that you know about these, but there are dozens of other bases that are like unto LDA that are in common use. Oops, I just realized. Let me put LDA back in its place. And then I'll show you a couple of other similar compounds. One that is unfortunately used quite a bit. I say unfortunately because I hate this stuff. There was a project I was working on for Dr. Singleton, in which I was forced to use this stuff, and because that was what I did try some other bases, but ultimately this is the one you're supposed to use. Let me put that in the right spot. There we go. And for whatever reason, this one seems to be usually sold as this sodium salt. Though I bet you could get your hands on the lithium salt too. This is a very long and awkward name, but sometimes we call this NaHMDS, which stands for sodium You're going to love this. Hexamethyl disilazid. But I don't really care if you know about this one, but you can see that it's the same type of idea. So in both cases, we've got the conjugate base of an amine in which, or of a secondary amine in which the two groups on it are quite bulky. And the result is a very strong but non-nucleophilic base. So, you got these big trimethylsilyl groups. They're kind of like church butyl groups and even the isopropyl groups in LDA. So these things are not going to act as nucleophiles. They are very strong but non-nucleophilic bases. And that's why these things are used. And then there's another one that I have to show you just because its name is so funny. I don't think I've ever used this one, unfortunately. It would be fun to use just because of its name. So in order to make sense of this name, one needs to be aware. I'm really crunking up, making this look at all symmetrical, aren't I? There we go, I guess. Let's see, what ion do they usually use? I think usually lithium is, I think this is usually supplied as the lithium salt. At this point, I'm just showing you these because the names are so outrageous. I have no idea why, but I've heard that people call this harpoon base. Don't ask why. I do not know why. If you wanted a more sort of official name, it would be lithium 2266 tetramethyl pipper. Yep, like that. And where that name comes from is piperidine is a 6-membered cyclic secondary amine. It's just a 6-membered ring with, it's basically cyclohexane except with NH replacing one of the CH2s. So that's piperidine. It's the reduced form of pyridine. The 2266 tetramethyl part, I think, makes sense. And it becomes piperidid from piperidine because you're looking at the conjugate base. So these are all similar reagents. I don't think I really plan to trot out one of these, though. You might run into it in OWL, but if you see anything like that, the thing to look for is, I would say, a bulky conjugate base of a secondary amine, or I should say, really, the conjugate base of a bulky secondary amine. These things are very, very strong bases and also completely non-nucleophilic because they're so bulky. They can only act as bases, never as nucleophiles. So you don't need to worry about it attacking anything and messing up your reaction. So, okay, enough with the funny names. But there is one other piece, since we still do have a little more than 10 minutes. That'll be good. That will leave just the alkylation stuff for next time. So it turns out that not all carbonyl compounds are created equal when it comes to forming the enolates. I picked up here in our example, or down here in our example, I had picked cyclohexanone, which is symmetrical. What if the carbonyl containing compound is not symmetrical? Well, then it depends which kind of base you use. So the idea is when you've got an unsymmetrical ketone or aldehyde, then it's going to make a difference which base you use because you can get two different enolates. In this case, one would look like this and the other like that. So, and lo and behold, I know you're all going to be thrilled about this. This is another one of those cases where you run into kinetic versus thermodynamic control. And again, the way you control that is by which base you choose. So let's see. It's going to depend on whether the base is very, very strong indeed, like one of these bulky secondary amine conjugate bases, or maybe hydride is a very strong base, or sodium amide would also fall into that category. Those ones are going to go to, basically we're talking here about bases that are so strong that once they pull off the proton from the alpha position, it's irreversible. And so LDA is certainly a base like that. Sodium or potassium hydride would be that type of base. Why? Because the hydride pulls the proton off, and then you get hydrogen gas, which bubbles out of the solution and is gone. So, so that would fall into that category too. But what about bases that are somewhat closer to these compounds in pKa? Here you're talking your alkoxide bases and hydroxide. Those are weaker bases, and they will not deprotonate quantitatively. And so as a result, if you were using something like ethoxide, so remember when you see NaOET, that means ETO minus, right? Remember the sodium ion doesn't play any role in the chemistry. It's just a spectator species. But what if we did that? What if we treated this compound here in ethanolic sodium ethoxide? Well, in principle, the ethoxide ion could deprotonate in either position. So, and it will only do so a little bit at any one time. And this would then have the possibility of the enolate picking a proton back up from ethanol. And so you can equilibrate. That's what we had the last time that we discussed kinetic versus thermodynamic control. And we said under thermodynamic conditions, you can equilibrate. And if you form the next intermediate, that can go in reverse and revert to the starting material, and you'll have another chance to get the more stable compound. That's what we mean by thermodynamic conditions, right? We're under conditions where everything is reversible. We can revert back to starting material and have another shot at getting over the higher energy barrier, but forming the more stable species. And that's exactly what happens. Eventually, little by little, you will build up a concentration of the thermodynamic enolate, the one that's more stable because the double bond is more substituted. Here we've got a tetrasubstituted carbon-carbon pi bond. And so deprotonating in the more hindered position is going to result in the thermodynamic enolate. And in order to do that, you want your base to be less strong. You want it to be an alkoxide base or maybe hydroxide. And so we'll talk about alkylations the next time. But I think you can already figure out if one were to treat this enolate with, say, benzyl bromide, then the enolate will attack the alkyl halide, expel bromide in this case, and you would get this compound as a mixture of enantiomers. So methyl down, benzyl up, benzyl down, methyl up. So, so that's how you would get the thermodynamic enolate, the one that is more stable by virtue of having an extra, or having extra substitution here, being a tetrasubstituted double bond instead of trisubstituted. What if you wanted to get the other enolate, the kinetic enolate? That's where these really strong bases like sodium HMDS or LDA or even sodium hydride come in. So let's say we did that. Here we have our LDA. Let's say we treated this. Remember, IPR is short for isopropyl. So you can write LDA like that if you want to. Now, this is now a very different critter, right? LDA, recall, is very bulky. So it's not going to go after the more hindered proton. It's going to try to pull off the first proton it can get in the least hindered position possible. So this is going to go after one of these protons over here. And once it does that, that reaction is irreversible. This enolate is now nowhere near a strong enough base to pull off a proton from diisopropylamine, which is the conjugate acid of LDA. So you will cleanly get this enolate. And now, when you treat this with benzyl bromide, you might get a little bit of enolization here. Oh no, I see what I did. I don't know why I made this bond wavy and not this one. But the idea here is that you're going to get a mixture of cis and trans. So you'll get somewhere where both the benzyl and the methyl group are up or down. You know, you'll get that mixture of enantiomers. And then you'll also get the other two enantiomers where they're trans. One's up and one's down. So that's, I think, what I meant to signify over here. But now you'll get alkylation in the more hindered position. I'm sorry, the less hindered position, because that's all you're going to be able to deprotonate from if you're using now a kinetic base. So whereas your thermodynamic bases were any that can deprotonate reversibly, such as alkoxides or hydroxide. If instead we go to these really strong bulky bases, or even sodium amide or sodium or potassium hydride, then you're going to get the kinetic enolate. This one is less stable because now you have only a tri-substituted double bond as opposed to tetra-substituted. But the main thing here is that forming that enolate is now irreversible, because once the LDA pulls the proton off, it's done with. You're not going to be able to get that proton back off it and revert back to the starting material. And now when you treat with, this enolate with our, in this case, benzyl bromide, you could use whichever electrophile you like. Now I'd expect that you would benzylate in the less hindered position. So you can see the difference in structure of these two. Sodium hydride counts as not bulky, but irreversible, right? Because once hydride pulls off the proton, first of all, it's a really strong base. So it's just going to go get the first proton it can. But no, yeah, I think you know this. Sodium hydride is anything but bulky, but it's irreversible. Once H- pulls off the proton, you have H2 gas, that bubbles out and is gone. So that's the key here, is that the deprotonation is irreversible with hydride. At least that's my understanding. So that's the big difference. No, it's a good question, but that's the big difference between these two schemes. On the one hand, you have a deprotonation that's reversible. On the other hand, it's irreversible. So this is something we're going to make use more of, I would say, in chapter 23. But that's the best way to think about this: is my deprotonation reversible or is it irreversible? And that will mean that you will get the thermodynamic versus the kinetic enolate respectively. So that's basically how that works. And since I still have 4 minutes, let's answer the question from before. Let's say that, let's forget about kinetic versus thermodynamic enolate for just a moment. Let's say that we first treated cyclohexanone with LDA and diethyl ether, and we got this enolate. There's only one enolate possible, so there's no issue here of regiochemistry. What if now we treated this with 1-bromobutane? Well, I think you can see what will happen. We already kind of gave the game away with the benzyl bromide. This is going to now do nothing other than an SN2 reaction. So if you need to brush up on that in chapter 11, by all means, feel free to do so. But that's all this would be. So just like that, and you would wind up with a butyl group where you'd had that hydrogen before. Oops. Oh, another thing I should mention, though I've mentioned it before, here's where it's starting to become relevant. Remember that the enolate is a resonance stabilized species, which means you can draw the other resonance form if you like, but let me put my butyl group on first. And so I'd expect that you would isolate something like that. So what I meant by the comment I just made was, oops. You'll notice over here, when I deprotonated with LDA, I pushed the electrons all the way through to put the minus charge in oxygen, but you don't have to. If you wanted to show this with LDA pulling off this proton and then putting the negative charge into carbon, in other words, the other resonance form, that's completely acceptable. Absolutely fine. That's up to you. That's up to personal preference. As I think I said, I tend to show the resonance form that is the minus charge in oxygen, but if you'd rather use the resonance form that is the minus charge in carbon, go for it. As far as I'm concerned, it's absolutely acceptable. Owl will be owl, but as far as I'm concerned, doesn't matter, whichever one you prefer. Well, it's given you a few minutes to think about it. So of course, LDA, as we just talked about, that's our kinetic base. That's going to go after the least hindered proton it can get at, which in this case is going to be this blue proton. So you're going to make the enolate on this side of the molecule, and that will now attack the benzyl bromide, and so you'll attach the benzyl group on this side. So be sure that you have the right number of carbons, don't lose a CH2. But there's your benzyl group. Of course, this is the CH, that CH2 was there to begin with. It used to be the methyl group. Meanwhile, if instead you used a thermodynamic base like hydroxide or an alkoxide ion, now you're going to get deprotonation in the more hindered position. At least that's where it will equilibrate to. So I would expect that you would get this as the product. And now you see now you see how I was lazy here. I purposely put two ethyl groups here so we don't have to worry about stereochemistry. That carbon's not chiral, so it's not an issue. So, but that's good practice for today's material. Oh, would there be stereochemistry in the products? No, I cleverly and lazily picked one where stereochemistry is not going to be an issue. But that's only by virtue of my having two ethyl groups here, right? Because now that carbon's not chiral. It's got two ethyl groups on it, so game over, not chiral. So I did that on purpose because I felt like being nice this time, and I didn't want any of us, including myself, to worry about it. Good, so I think that's a reasonable place to stop. And also kind of a look ahead to Friday's material. So other than that, we actually are out of time. I hope we made good use of class material. So I will see you on Friday from my hotel room. We'll still have class as usual. I mean, I'll be staying in the Woodlands, which is outside of Houston. It's not in the middle of nowhere. I've been in that hotel before. They should have good internet access. I guess if something goes wrong, we'll all know. If it goes terribly wrong, I won't be able to email you, but I anticipate there won't be a problem. Should that happen, then I'll make a YouTube lecture for you like I did on during that winter storm, but I anticipate we're going to be fine. So have a good day. We'll see you all on Friday.
Dr. Wass, quick question.
Sure.
So because we have material that we still have to cover from chapter 22 on Friday, is the OWL deadline going to be moved to next week, or is it still going to be this Friday?